Welcome to the class Deep Learning in Artificial Neural Networks. In this video, we take a statistical point of view and ask whether there is a good reason to work with a sigmoidal function as an output unit. So, we are in the context of a statistical setting, and so the idea is that this output unit here gives the probability that the input that we apply here belongs to the class. Which is the same as saying, well, if we had an additional labeling module that generates labels stochastically, then this is the probability that the label would be +1 given this input x in the input. So this x, this y here is supposed to be a probability now, and therefore it must be between 0 and 1. Good. There could be many functions. Intuitively, well, this kind of smooth function is probably better than such a hard threshold function, because then we lose the probabilistic nature. It's basically always +1 on this side and always 0 on the other side. So the question now is, among all the possible smooth functions that go from 0 to 1, is there a natural choice? Is there a best choice for g of a? So we take a statistical point of view, which means we take the output as a probability. So we write this output of the network, y hat 1, as p of c1, probability that belongs to class 1, that this input x belongs to class 1. And then we just apply Bayes' rule and find that this is p of x given c1 times p of c1 p of x. Now, well, this is just one way of writing the Bayes rule. The two together really are the joint probability p of x and c1, and I divide by p of x. Well, but p of x can be written as a sum. So it's p of x c1 and then p of x c1 plus, well, all other possibilities should appear in the denominator, but there's only one other possibility, and that is that this data point is not part of the class, they're not indicated here by a horizontal bar. And now I can divide this expression by p of x c1. So now I have 1 divided by 1 plus p of x c bar 1 divided by p of x c1. So then we can write this as 1 plus b, where b is this term here. Now, what are the values that b could take? Well, b must be positive because the probabilities are both positive. And, well, it can go up to infinity if one of the this probability here is very small, then b can become very big. Now, if you work with such a parameter b, then implementing the constraint that it must be positive, b must be positive, is not impossible, but it's kind of difficult to treat this analytically. Maybe you need a Lagrange multiplier and so forth. So another possibility, instead of putting it as a constraint, is to just replace the b by a term, and now I write it in the same color, e to the minus a. So now a can go from minus infinity to plus infinity. So no constraints on a, and otherwise it's just the same. So we just define e to the minus a equal to b and b equal to this. Now that means that if we compare these two here, that means that a is the logarithm of the ratio p of x c1 and p of x not in class C1. Now let's come back to what we started out to do. We said we want a sigmoidal function, an output function that goes from 0 to 1, which is the case here. It's a probability. And this function now, as a function of this a, the activation variable of the neuron, has now a nice sigmoidal shape. Let's plot this. So this is a hand-drawn plot of this function. You see a typical sigmoidal shape, and that's again the definition. So this is the definition of the standard sigmoidal that's usually used in the output layer of a neural network in the context of a statistical interpretation. And if you use this function, then you may interpret your total input A, or the activation, the drive of the neuron, as a log probability ratio. The logarithm of probabilities are sometimes also called the evidence. Then the log probability ratio can be interpreted as the evidence in favor of assigning input X to class C minus evidence against assignment of class C to input X. Here a plot, the actual plot of the function. It's a nice smooth function. It goes has values between 0 and 1. I like to point out this one here. If you choose a value a equal 3, then you roughly get a value of 0.95. The whole thing is symmetric. So if you choose a equal minus 3, you get about 0.05. So here it's roughly 5%, here it's 95% in the context of interpreting the output as a probability. Let's sum up. Why sigmoidal output? Well, we are in the context where we want to interpret outputs of a network probabilistically. So if we interpret the output as the probability that an input X belongs to class C1, then this activation variable A of the sigmoidal output unit of that form can be interpreted as a log probability ratio.